Hi, it's Mr. Mac, and in this video we're going to be looking at motion in a gravitational field. In particular, we will look at the work of Johannes Kepler and his 3 laws of planetary motion, and how that has revolutionized our understanding of the planets in the solar system, in fact of how planets move in any system.
This is Mr. Mac. He can explain things really well and is a lot of fun to watch. You can subscribe to Mr. Mac's Physics channel. You will find mathematics problems, science demonstrations, astronomy and space pics, physics calculations and simple explanations of advanced concepts.
What did Kepler discover about the planets? We are learning to describe and analyse qualitatively and quantitatively motion in a gravitational field, and we will be able to solve complex questions using, as we'll see in this video, Kepler's laws of planetary motion. So who was Johannes Kepler? He was a key contributor to the scientific revolution according to Physics Today, and according to Britannica, a German astronomer who discovered 3 major laws of planetary motion. He has been called a man of science and a man of God, and it's easy to separate these 2 aspects of his life and concentrate on one or the other. But for Kepler, his scientific achievements were a result of his deep faith in God. So when we look at planets going around the Sun, and we analyse that very carefully, up until Kepler, everyone thought that planets like the Earth orbit in a circular motion. Copernicus based his heliocentric model on circles and lots of circles. But in reality, if we find the Earth orbits the Sun in an elliptical orbit with the Sun at one focus of the ellipse. In Astronomia Nova, a book that Kepler wrote, he developed a model of the solar system, and you can see on the right-hand side a drawing with the models from Copernicus, from Tycho Brahe, and from Ptolemy. Ptolemy was an ancient Greek. And he showed that all 3 models were indistinguishable on the basis of observations alone, just by looking at errors of measurement with 8 degrees of arc as an error. And it was probably the first time that errors of measurement were actually used in a theoretical sense like this. And he presented conclusions regarding the work that he did on the planet Mars, although in this work it's called a star, as you can see from the title, if you can read Latin. And he used the work of his predecessor, Tycho Brahe, with lots and lots of observational data. And he concluded that the orbit of Mars was not a circle, but an ellipse. And he asserted that each of the planets that orbit the Sun has an elliptical path at which the Sun is at one focus. He also stated that a line from the Sun to a planet sweeps out equal areas in equal times. This is the so-called area law. Here's a graphic showing the area law with a planet orbiting the elliptical path. And you can see the aphelion, which is the farthest point, it seems to go slower. And then when they get to the perihelion, the nearest point to the Sun, the planet seems to go faster. And the blue triangle or sector is the same area throughout. So even though it's really long and skinny, the area of that sector is the same as the area of this sector, which is short and squat. Aphelion comes from 2 Greek words, aph meaning away from, helion, the Sun, peri, next to the Sun. So what were Kepler's laws of planetary motion? He developed 3 laws which described the motion of planets across the sky. And the first law was the law of orbits, which we've already mentioned, that all planets move in elliptical orbits with the Sun at one focus. The second law is called the law of areas, and that is that a line that connects a planet to the Sun sweeps out equal areas n equal times. And the third law is the law of periods, saying the square of the period of any planet is proportional to the cube of the semi-major axis of its orbit. To put it in algebraic terms, t standing for the time it takes for one orbit, or the period, capital T squared over r is the distance from the centre to the outside of the orbit, it's like a radius from the centre of the ellipse. So t squared over r cubed is a constant for every planet in the solar system. Kepler's laws were derived for planets orbiting the Sun, but they also apply to satellites orbiting the Earth, or moons orbiting Jupiter, and any other planets, including exoplanets orbiting distant stars. So how can you work out t squared on r cubed? How did Kepler do it? He actually did a lot of work on logarithms, and this is not the place to go into depth about what a logarithm is, but suppose that you suspect that you have a measured quantity, capital Y, that is somehow related by a power law to another quantity, capital X, that is, the quantities satisfy the relationship y to the m equals ax to the n for some integer values of unknown parameters m and n, and a constant a, which is a multiplier. And if you have enough data for x and y, how can you discover the values of m and n? Well, Kepler knew about logarithms. And so if you take the log of both sides, it can be base 10, it can be base e, it can be a base anything really, but let's keep it at base 10, then the power is the same as multiplying m log y, and that will equal log of that constant a plus n log x. And you'd have to look up your rules of logarithms to just check that that's the same thing. Dividing everything by m, you have log y equals 1 on m log a plus n on m log x, and that first term on the right-hand side are all numbers. It's simply a constant, so we can replace that with just a capital C for constant. And now we can see that what we have is in the form of y equals mx plus b, where y is equivalent to log y and x is equivalent to log x. So if you transform the data, plot the points on a scatter graph, you can draw a line of best fit, and the slope of that straight line will give you the ratio n on m. We've done this in another video, and it turns out to use the planets that you get 3 over 2. The gradient's 1.5, but 3 on 2 then turns out to be the powers of this ratio, this relationship, which is what Kepler discovered with t squared on r cubed. So here's worked example 3, 2 satellites sharing the same last HSC question. And it says 2 satellites share an orbit around a planet. One satellite has twice the mass of the other as shown in the diagram. Which quantity would be different for the 2 satellites? Now, when we look at this, it's a multiple choice question with A, speed, B, momentum, C, orbital period, or D, centripetal acceleration. My students tend to say this is a multiple guess question, but really we can work through this logically and eliminate those that are impossible, and we're left with the one that is the correct answer. If we start with A, the speed, and think about just circular motion, V equals 2 pi r on t, which is the same as 2 pi r on replacing t with the square root of 4 pi squared r cubed on gm. That's rearranged from the formula sheet. Simplifying equals square root of gm on r. So it depends only on big M, that's the mass of the planet, and r, the orbital radius. So if we're changing the mass of the satellite from m to 2m, it has no effect on the speed. For B, momentum is given by the formula P equals mv. So using what we just found, P, the momentum, equals little m times the square root of gm over r. And you can see that depends on the mass of the satellite m, big M, mass of the planet, and the orbital radius. So that means if we double the mass of the satellite, it's going to affect the momentum. Well, let's, for completeness, look at C and D. For C, we need to use Kepler's third law, r cubed on t squared equals gm on 4 pi squared. So rearranging, t squared equals 4 pi squared r cubed on gm. And again, you can see it depends only on big M, the mass of the planet, and r, the orbital radius. For centripetal acceleration, again, we're going to use circular motion as an approximation. A equals v squared on r. We found v. We square it. It's gm on r squared. It depends only on big M and r. And you can see I've circled. The correct answer is momentum, because the quantity that would be different for the two satellites with different masses would be their momentum. Here's worked example 4, accounting for changes of velocity of a comet. It's a past HSC question. And the question is, the orbit of comet is shown in the top left diagram. Account for the changes in velocity of the comet as it completes one orbit from position P. P is the aphelion, the farthest point from the Sun. And here's a sample answer. All planets and comets in the solar system move in elliptical orbits with the Sun at one focus, is Kepler's first law. So the velocity of the comet will change direction, making one full revolution of directions in one complete orbit. So simply looking at direction, remember velocity has magnitude and direction, the directions change in a full 360 degrees as it does one complete orbit. Additionally, Kepler's second law states that a line that connects a planet to the Sun sweeps out equal areas in equal times. Thus, the comet will travel at a higher orbital speed when it is closer to the Sun and at a lower speed when it is farther away. When the comet is farther away from the Sun, it also has a greater gravitational potential energy and a lower kinetic energy. As the comet moves toward the Sun, its gravitational potential energy is converted into kinetic energy, which is consistent with the law of conservation of energy, that energy can neither be created nor destroyed, but transformed from one form to another. This increase in kinetic energy results in an increase in velocity as it approaches the Sun. Well, here are the comments from the markers. Accounts is for the changes, that's plural, and so you have to account for many changes, not just one, and the velocity of the comet to get the 3 marks. If you just simply provide a reason for a change in velocity, that's 2 out of 3. If you provide some relevant information, that's 1 out of 3. So it's easy to get 1, but you need to have a full detailed answer to account for all the changes in the velocity of the comet to get 3. Here's worked example 5, which is deriving Kepler's third law. In other words, how does it work? And on the top left, you can see a diagram plotting the cube of the semi-major axis against the square of the orbital period, and it falls into a straight line, which is very neat. But how does it work? First thing we need to state, and you would state this in an exam, is that if an object is orbiting, it is approximated by circular motion. Simply because we have the formulas on the formula sheet for circular motion. And we know that the magnitude of centripetal acceleration is v squared on r, so the magnitude of net force is mv squared on r. We also know the magnitude of gravitational force is big G, big M, little m over r squared, using the Newton notation on the formula sheet. Now at this point we need to understand that Kepler didn't know gravitational force. He assumed it was some sort of perhaps magnetic force or some sort of result of light emanating from the sun that caused the planets to go round in their orbits. It wasn't until Sir Isaac Newton came up with his law of universal gravitation that we know so well that we can actually use that to derive Kepler's third law. So here we go. Let's equate the forces. So the force due to gravity, big G, big M, little m over r squared, equals the force, net force to the centre of the circle, mv squared on r. And you'll notice straight away that there's a little m on both sides. We can cancel. There's also an r on both sides at the bottom that we can cancel. So we're left with big G, big M on r equals v squared. And remember that the magnitude of orbital velocity is v equals 2 pi r on t. So now we can replace the v with 2 pi r on t, making sure we square it, put it in brackets. So we're left with big G, big M on r equals 4 pi squared r squared on t squared. All we have to do now is rearrange to get t squared on r cubed equals 4 pi squared on big G, big M. That's Kepler's third law. Well, how can we use Kepler's third law? Here's a picture of a satellite going around the Earth, and if we're given Moon's orbital data with its orbital radius and its period, and Earth's data, we can calculate anything really. And the question is, in this case, what is the average time taken for a satellite to orbit the Earth at an altitude of 500 kilometers from its surface? So the first step is always data. There's a trick in this question. Altitude, let's call it h, equals 5 times 10 to the 5 meters, remember, SI units. And since the satellite and the Moon both orbit the Earth, we treat it as the Earth system. They both have the same ratio value for t squared on r cubed. So the orbital radius of the satellite, that's radius of the Earth plus its altitude, we can see the calculation begun there, and that will end up equaling, once we add those two together, 6.87 times 10 to the 6 meters. So we have t squared for the Moon over r cubed for the Moon equals t squared for the satellite over r cubed for the satellite. Now, please note, that's not on the formula sheet, but you have to know it and apply it to different systems, whether it's the solar system, in this case the Earth system, it could be the Jupiter system, it could be a mysterious planet X system. But whatever you do, remember t squared of r cubed is always the same. Rearranging, we get t squared for the satellite equals r cubed for the satellite times t squared for the Moon over r cubed for the Moon. Simply substituting, calculating carefully, we find that the period for the satellite, that's capital T, is 5.65 times 10 to the 3 seconds, correct to 3 significant figures. And if we wanted to know what that meant, it's roughly an hour and a half, or an hour and 34 minutes and 7 seconds. And that's okay. That makes sense for a satellite orbiting 500 kilometers above the surface of the Earth. Well, what about the International Space Station? If you go out tonight after sunset, for the first 2 hours or so, you might be able to see satellites moving across the night sky. And one of them might be the International Space Station. Go out tonight and see if you can try and see it. Here's a question. The International Space Station orbits the Earth with an orbital period of 92 minutes and 45 seconds. By the way, that's very fast. Just over an hour and a half to go around the whole Earth. Question part A is, what is the average altitude in kilometers? Here's the data. We know the mass of the Earth from the data sheet. We know the radius of the Earth from the data sheet. We're given G in the data sheet. We're given H in the, we need to find out H in the question. And we're given the period of the satellite is 92 minutes and 45 seconds, which is 5,565 seconds if you do the calculation. We need to find the orbital radius before we can find its altitude. So we use, in this case, r cubed on t squared equals gm over 4 pi squared, straight from the formula sheet, noting that capital M in this case is the mass of the Earth. So r cubed equals gm e t squared for the International Space Station over 4 pi squared. Substituting and taking the cubed root, and we need to be really careful at this point that we pick the right button on the calculator. We calculate the orbital radius. There it is in meters, but there it is also in kilometers as 6,796 kilometers. That's not the answer to the question. So we need to make sure we answer the question. The question is, what is its average altitude in kilometers? So we need to subtract off the radius of the Earth. So the height or the altitude of the International Space Station is 6,796 minus 6,371, again from the data sheet, equals 425 kilometers. So it's really low Earth orbit, which is why they have to keep adjusting the orbital altitude of the International Space Station. Well, part B says calculate the tangential speed of the International Space Station. If it goes around the Earth every hour and a half or so, how fast is that? Well, let's use v equals 2 pi r on t. We have all the information, so substitute what we've just found, and we come up with an orbital tangential speed, 7,673 meters per second, or roughly 7.7 kilometers per second. It was very fast. And the astronauts and cosmonauts in the International Space Station do not spend their time just gazing down on Earth. They're doing scientific experiments, other things to do with their living routine. But also, when they're looking down, they're passing over the Earth very quickly. And the last example is worked example 8. Please note the photo. I'm very pleased with this photo. I took it with my wife's Lumix digital camera with a zoom lens when we were on holidays at Mooloolaba in Queensland, Australia. And you can see quite clearly 4 dots around this blurry dot. The blurry dot is Jupiter, and these are 4 moons of Jupiter that I took with a camera. Jupiter does not look like the beautiful picture in the top, which comes from space images from planetary.org. Here's the question. Ganymede is the largest of Jupiter's moons. It has a mass of 1.66 times 10 to the 23 kilograms and an orbital radius of 1.07 times 10 to the 6 kilometers and an orbital period of 7.14 days. Now those are Earth days, which is the same as 7.18 times 10 to the 5 seconds. Using Kepler's third law to calculate the orbital radius in kilometers of Europa, which is another moon of Jupiter, which has an orbital period of 3.55 days. Now, this is a textbook question, but remember that the formula that we need is not on the formula sheet. To write down the data, group together Ganymede's orbital data, as I put there, and Europa's orbital data. And use this formula, t squared on r cubed for Ganymede equals t squared on r cubed for Europa. Then substitute carefully. Please note in this formula, we actually don't need SI units because where there's a ratio, it cancels the units. And it's ratio squared in this case over ratios, the units cancel. This is the exception to the rule of bringing everything to SI units first. When we rearrange, we're going to put the orbital radius for Europa as the subject. So RE cubed Well, you can see what it is there. We take the cubed root of that, and we end up with, doing a careful calculation, 6.71 times 10 to the 5 kilometres, correct to 3 significant figures. And work example 9. What is the altitude of a geostationary orbit? Now, the government wants to put up a geostationary orbit. It takes 24 hours to go around the Earth. Where must it be located? How high? There's the data. There's t squared on r cubed equals 4 pi squared on gm. And we rearrange to get r, substitute, take the cubed root, and we find it's 4.23 times 10 to the 7 metres from the centre of Earth. But that's not the answer. How high is the altitude? We need to take away the radius of the Earth, and we find that it's 3.59 times 10 to the 7 metres above Earth's surface. Now we've seen Kepler's laws of planetary motion. What was his view of the universe? Well, he was a committed Christian. In other words, he was committed to Christ. He had conversion just as Martin Luther had had conversion and come to know the forgiveness of sins through Christ's death on the cross and his resurrection. Kepler came from a poor family, but he was very gifted, and so he won scholarships for his education that allowed him to go to seminary and university. He studied at the University of Tübingen, which is outside of Stuttgart. That's now in modern-day Germany. And when he was there, he studied divinity, that's Bible and theology and philosophy, for 4 years, but then he was persuaded to change direction to study astronomy. And you can see on the top right, he had an idea of the planetary orbits being based on the 5 Platonic solids. He was infused with Plato's philosophy. He then, after understanding a little bit more from Tycho Brahe's observations of the orbits and what he derived from his observations, those 3 laws of planetary motion, his view really changed to a view that said those laws of nature are within the grasp of the human mind. God wanted us to recognize them by creating us after his own image so that we could share in his own thoughts. In a sense, we were thinking the thoughts of God after him. And that was Kepler's view of the universe. So we've seen some of the work of Johannes Kepler, his 3 laws of planetary motion. I'm Mr. Mac. Thanks for watching.